It seems always the case that something like validation is put in the way before beer. So we have to persuade that it's still an important subject. Anyway, it's called Progress and Problems in Cryo-EM Validation. Thank you very much to the organizers for inviting this. And in fact, I was encouraged to speak on some of the recent community results from the electron microscopy validation task force. So community agreement already might represent some form of progress. Then I'm going to talk a little bit about outputs of the UK validation network, and then we'll on to some subjects of future interest. Okay, this is a general scheme for map and model validation problems. Is that cursor appearing? Good. So I think now with the high resolution maps where you can build in all the details, if you haven't put them in from the start, there's a good sense that everything is correct. There are still some of the same principles that applied in the past to low resolution maps still generally apply, such as agreement between the projections and image data, whether class sums or individual particles. When it's a low resolution map, you still, since it's still blobby, you might want to prove that you have the right angular distribution, as you would for a high resolution map. There is a method called tilt pairs, which might be important in validating a structure at that resolution. And of course, the Fourier-Shell correlation is usually reported. And at that resolution, maps can be validated by fitting models. And there's always the interchange between the two. At low resolution, the model might often come from another source. And since the information is not inherent in the map, the geometry should be ideal. And you nevertheless may fit as rigid bodies or flexibly fit, provided you're not introducing more degrees of freedom than the map can support. And of course, the map model FSE applies there. So at high resolution, again, even though all those things may come into play, it seems that the map might have those features. And then maybe the focus might be on the resolution assessment, although there is the concern generally of how to validate very small features in high resolution maps that may be important to the biology. And on the model side, I think we still take the guidance for the geometry of models from the X-ray community. There is the global map model FSC, but perhaps even more important is the local agreement between parts of your model and the map. So anyway, this framework works for some things, but not for others. A lot of the consensus on practice in the field up until now still dates from this validation task force meeting in 2010, for which there was a publication and it recommended some of the things that everyone applies now. But a lot has happened since then. Though there haven't been, well, I'll discuss another meeting in a moment that happened recently, but in the meantime, there's been, aside from just the community working away at the problem, there's been some map and model challenges and model metrics challenges, which have been informative in this area. So for map deposition, there's been the idea that half maps, unfiltered and unmasked from the reconstruction program you're using are a good thing to deposit in addition to a full unfiltered map. But of course, you can deposit any other maps that might be important to supporting your study. Now, with the huge developments over the last decade, some of the problems have shifted. This is just one example from Donald Benton's work on the hemagglutinin, where you have a beautiful high-resolution part of the molecule, and you have a part which is the transmembrane region, which is flapping around. And how do you validate all parts of such a map? So the real problem now is the non-uniform resolution and how to fit models and also how to report it. Of course, it's never just one map anymore, it's multiple maps from classification in a given experiment or possibly between experiments. We know that in order to see the features, you have to enhance maps for model building. That brings up the related questions of how one assigns atomic displacement factors, or sometimes referred to as P factors, to a model. What is the map that should actually be used in refinement? And I typed this in while listening to the last talk, when to use density modification. So, map and model deposition for multiple conformers and focused refinements. We have the idea of a consensus map, which might somehow be an average of everything, and we might have chimeras, which will be constructed combinations of all the image processing that it's hard to say where that exists in reality. The idea that for focused maps, one should be communicating to colleagues what the refinement mask is. There should be an idea of what the relative transformations are between those focused maps. That is, everything should somehow be in the same coordinate system so that we can understand and validate. That's also true for conformers. And then the masks associated with every refinement. Okay, so these are general ideas, which I think so certainly everyone here is working with and applying. Our work ends up being closely associated with the organizations such as CCP-EM and EMDB, which help solidify consensus on things. And I'm now going to refer to outcome of a meeting, which was a new validation task force hosted by the EMDB and worldwide PDB. And here's a snapshot of some of the people, and I should say there's Gerard has given a talk on this, on some of the outputs. I might emphasize things in slightly different ways, and this is the idea that things that influence both deposition and how validation reports are put together. So there are. So I'm going to describe broadly some of the outcomes of that. Of course, there will be a paper describing all of it in detail and more. But in a nutshell, there's the feeling that there should be a deposition matching almost every figure in the paper, because that is an experiment, and that needs to be supported by data. As mentioned previously, the deposition of the half maps, in addition to the full unfiltered maps or other maps you want to deposit, it will now be mandatory. And the critical thing is that everything, most validation procedures and ways of enhancing maps, you will make use of those. So in order to reproduce calculations, we need those. And then also deposit masks associated with any Fourier shell correlation calculations. There are composite maps can be constructed from individual maps. In other words, that's something which is being embraced, but it'll have to be clearly labeled on deposition. Again, all maps and models should be deposited in this in a common coordinate system. Of course, we now all struggle with the idea that for a deposition for every figure, this will be a huge activity. So the idea is that in the future, there has to be some thinking by the databases how ideally things could be grouped according to the investigation, which was the key word we were looking for earlier, that all of these are part of an investigation. So you might be depositing an investigation rather than individual maps. Obviously, that's a can of worms, but we can discuss that over beer. Local resolution maps, maps that display the local resolution are something which may be important. There is at the moment not a consensus on the best local resolution type calculation, so a number are being tried. Of course, map model FSCs, and again, the geometry for this sake of this presentation will be what's been specified by the X-ray protein structures over many years. So these meeting led to recommendations on validation reports, something that Gerard referred to. I'll also show a slide from the EMDB on how there's a three-tiered system for these validation tools. It's pretty clear that in addition to local resolution, for which there needs to be consensus, their map model fit recommendations for local scores, clearly one of the most important things in validation now. There are a number of possible scores. I think the idea is that those are now being studied together, something that with deposited half maps might actually drive that that research. So the point is, it's critically important, but not a consensus on any given set of tools yet. Also, the idea of map anisotropy, which we heard a bit about from the EM Hanser talk, is also very important both on the map side and model side. And there's the idea that the 3D FSC could be, for example, described by Liumkes, should be somehow integrated. But at the moment, there doesn't seem to be a complete consensus on how that should be reported. So that's something important to think about. Generally, there needs to be a capture of validation from experiment and image processing, which we ultimately might end up in depositions, and then also an idea of what restraints have been used in refinement. And I think perhaps other speakers have emphasized that, the idea that using both a metric as both a target and as a validation measure runs into problems. Okay, so anyway, those are the highlights of what I guess is agreed upon and the databases implement. Of course, there are probably a lot of other ideas as discussed that are, should possibly be incorporated into that relatively soon. So now I'm going to shift to describe just some of the outputs of a Wellcome Trust funded validation network in the UK. This involved colleagues at CCP-EM, Martin Wynn, Alan Roseman at Manchester, Elena Orlova and Meyer Topf at Birkbeck, Gary Murshidov at the LMB, and Ardan and Gerard at EMBL EBI. And these are postdocs, Valeri, Mauro, Agnel, Jay, Lucas, and Rangana, who've been involved in various things. And I'm going to present some of the outputs of that work. Generally, as with the whole validation effort, the goal was to come up with tools for consistency and uniqueness of cryo-EM maps with respect to underlying data and the consistency of atomic models with the cryo-EM maps. And we had a meeting, a live meeting, which just was before that EMVTF meeting. And of course, we had planned to have another meeting, but that live, but that ended up happening for obvious reasons online, and that was cryo-EM validation in the age of SARS. And of course, one of the things we've seen has been the contribution of structural biology to the issues related to the pandemic. And strangely, that burst of activity has also focused a lot on validation issues, and so that's been interesting and has driven thoughts and results. So one of the first things which was mentioned earlier, that there are the validation reports now include a lot of information. I'm sure those of you who are depositing will be familiar with these, and this has been work of, in addition to EMDB, Jie Wang in particular, who's, I understand, has a poster on these things here. The idea that how do validation tools get set in stone? Well, the idea is that there will be some that are part of the validation reports. That's sort of the third tier. There are others that have been viewed as successful and are added as metrics to EMDB entries, but then there will be a lot of validation analysis tools. I don't know where that red cursor is coming from. Very interesting. It's not me. So, but the point is, anyway, our colleagues at the EMDB, they also have a procedure for bringing these validation tools online and get it so the community can assess them. And in addition to the deposition side, of course, our host for this meeting, CCP-EM, is building these pipelines for structure determination, and of course, validation has increasingly been part of their focus. And there are a lot of tools here, which I just mentioned. Because we've been working directly with Agnel and Martin on the grant, I wrote it down this way, but he's been working closely with colleagues in the community generally, and also his colleagues at CCP-EM and EMDB. So just wanted to highlight a few things that I thought are important emerging from this work. Certainly a subject which, I mean, we don't mention in the context of every EM determination, whereas it's a routine in X-ray, is the importance of cryo-EM difference maps. This is taken from their publication listed here, which describes methods for difference maps, building on tools from a number of years. But the idea that the difference maps are critically important for interpreting the biology, because what we're talking about is being able to sense the difference between states or between, that is, conformers. But then there's another very important side, which is when you have a model and the map, we want to see how those differ. And that's clearly an important thing and something which needs further work in this field generally. Along the lines that validation requires detailed comparison of the maps, I think that sometimes the model assessments are rushing ahead of the maps. Rangana, along with Garib at the LMB, as part of this project, have been developing EMDA, which is a likelihood-based tool for map and map model superposition. And it's pretty clear that these sorts of approaches are important for being able to validate the highest resolution maps that are now the product of cryo-EM. And this is one of their use cases of it is a map which had an unmodeled region right here. and you can see that's right here. And by using this correlation between their map and the model, that you can see how that stands out, and then how that same score will disappear when that region is modeled in. So that's a general utility. And as far as this particular map, I think we're going to hear some of the biology behind that from one of our speakers tomorrow. For a long time on this table was the importance of being able to take a map and evaluate its symmetry. And again from Rangana, Garib, and co-workers, there's been the ProShade tool in the past, and now further enhancements in order to be able to identify the symmetry clearly. Oops. Okay, then Alan Roseman and Valery Tintorenko have also been working on volume matching tools within a framework called DocEM V, and that's something that is also a part of CCP-EM, and that's with the general idea of globally aligning maps and being able to do searches of fragments against map, and we think that will also be important in the world of in situ studies. Okay, so I wanted to just return briefly to this subject of tilt pair analysis, which something I worked on in the past with Richard Henderson. And there are various tools for it, including those listed here. But for a low resolution map, this has been valuable because, as a number of speakers have alluded to, including Tim, the danger of maps aligning to noise in the data is an important one, both at low resolution and at high resolution. And in the low resolution case, you can confirm against the worst possible case that all of your angular assignments are wrong and your map is wrong by this consistency between angular assignments in an untilted image and in a tilted image. So we've been wondering about what might be the utility of this in a higher resolution world for either optimization or validation. So I'm taking an example that we have applied it to from our studies of retroviral capsid assemblies, which have been in collaboration with Ian Taylor's laboratory. And these structure was solved and published by Oliver Acton, my student, and with a lot of help from our structural biology platform, and in particular, Andrea Nans on some of the experimental procedures I'll describe. So what's interesting here is that this is a large macromolecular assembly with a lot of signal. It comes from this this protomer assembling into the different symmetries, and you can see within the context of these assemblies, we can actually resolve even the flexible linker regions quite nicely, which I've shown here. So here we have a t=1 and then various other higher symmetry examples. So this is a heterogeneous data set. So we were interested in seeing, well, can we apply tilt pairs to this? And of course, when you sort things out and you associate your tilt pairs with any given map, you can independently validate those maps as shown here. The idea is if there's a single peak on this plot, it means that there's a perfect angular agreement between the untilted and tilted particles. And this has been the work of Lucas Siemens under the grant, but with experimental work by Andrea. So one of the things Lucas was very interested in, could, from the particles that end up in individual classes, could you also do this tilt pair test? And the idea is that this is a particular map, and from a data set in which there's a tilt pair for every pair, there is for this particular class in that data set, there is a clear signal in the tilt parameter plot. Oops. But for this class, it clearly it doesn't as outstandingly agree with that map. So this is referring to the talk earlier by Dari Comenius that who was talking about interesting machine learning procedures for evaluating 2D classes, which are the good ones. This we thought is an objective procedure as well for identifying which classes are assigned to a model. And although full data sets to match the high resolution of your whole data set might be a bit of a task, we found that if you can just add in a few tilt pairs and match them up with the classes, just that very small bit can identify classes, for example, for this D5 example, which are strong or weak. Okay, now this is moving from the idea of these tilt pairs. We know there's an increasing focus on tomography, and of course there we're recording many images of the specimen, and of course the idea of, in many instances, doing tomography and single particle is informative on some of the validation issues. In addition, there are hybrid schemes which where you include, in addition to the tilt series, an extra high dose image just flat on, which might provide different sorts of information. And just for our enthusiasm for all of these new approaches, Tom Calcraft, my student, and I wrote a little review on this. But and in this last picture connects with one of the sort of experiments Tim Grant was describing, the idea that there's an incredible amount of even cellular information in a 2D image of a cellular specimen, and that you can match particles against that. And one of the ideas they expressed, and we're trying to convey here, is that actually, because the noise properties will be different in single images versus in these tomograms, that there are new opportunities for simultaneously validating what comes out of these more complex data collection strategies. Okay, so then for the future, it's clear that validation of subtomograms, which are historically of lower resolution but are catching up, will have some similarities and differences to the single particle validation. One of the things is because they come from a crowded environment that poses certain problems, but people are now working on and in the literature on how to address those problems. There is a validation possible by mapping your objects back into the tomogram, to the original tomogram, and I know that's something I know Giulia Zanetti has been enthusiastic about, and maybe we'll hear something about that from her tomorrow. Generally, there's all these machine learning methods and how to mesh those with some of our conventional validation procedures. We'll see. And then also something very important picked up by the last speaker is, the astounding success of the theoretical structure prediction clearly can be linked to the validation of our cryo-EM models, and we'll learn a lot from that. And with that, I think I can finish. I tried to thank them on the way through, but thanking the colleagues at EMDB, at CCP-EM and on the ground for a lot of interesting discussions and work. Thanks.